Well, we now have a good handle on the universal law of gravitation. What I want to do in this video is just show you the versatility of the results and how many wonderful little other results we can get basically solving for variables. So it's just going to be some algebra, and yet I'm trying to emphasize the overall idea so you don't think you have to memorize so much, but you can solve many problems, particularly by just a little bit of manipulation. This is the great big fundamental concept of the unit, that the centripetal force required to follow a orbital trajectory is provided by gravity and gravity alone. So now we have an equation for gravity, and we already had equations for centripetal force. Set them equal, solve for what you need. So, orbit velocity. To start with, let's go mv squared over r, there's an fc, is gmm over r squared. This will always be what we write for fg. What we write for fc can be mv squared over r, or m 4 pi squared r over t squared, or 2 pi v over t as well. We can do that, but usually we don't. All right. Notice what cancels here, and we get orbital velocity equals square root of gm over r. We use that quite a bit, so this is one that, again, you don't need to memorize. You might have this memorized in spite of yourself after using it for a while, but look how easy it was to derive. Now we also know mv squared over r is mg. This is just, again, gravitational tug. If you happen to know the g field, like if the problem says that a satellite is orbiting near the surface of the Earth, then g is just the 9.8. We don't have to worry about solving for g. In which case, orbital velocity, square root of rg. Now, what about the period? Well, we do the same thing, but as I said, now we pick the fc that has period in it, and that's gmm over r squared. And it's also mg, so we have three different things here, and there's a lot we can get out of this. What should we do first? First, let's just divide out the little m. Notice the little m never has anything to do with the orbital radius, or the period. Now I'm going to invert the whole thing. So there's everything inverted, just to get it in a better form. I'm going to solve for t squared here, and basically multiply this by this, so we get r squared times 4 pi squared over gm. And so t is equal to 2 pi square root of r cubed over gm. Or we could equate this and 1 over g if you happen to know the g, which is less likely, but just showing you, again, some of the many possibilities. We can solve for t, 2 pi squared of r over g. Doesn't that look like a familiar form again? 2 pi squared of m over k, 2 pi squared of l over g, 2 pi squared of y over g. We've encountered in the past. Now in an orbit, we have period as 2 pi squared of r over g. Let's now check out orbital radius. Fc is equal to Fg. We can write our centripetal force equation, equate it to gravitational tug, and just mg also. So m's go away. We get 4 pi. Okay, what I'm going to do now is I'm going to take this and bring it up here. So we get r cubed over t squared, and 4 pi squared is just gm. So we get r cubed equals gmt squared over 4 pi squared, or r is the cube root of gmt squared over 4 pi squared. R is equal to gt squared over 4 pi squared. So just setting these two equal. Okay, so that's pretty simple. And finally we can say, we can set these two equal if we want. R squared g equals gm. R is square root of gm over g. All right, so you see all the possibilities, and there are more. Now, a point to be made that will be useful for problem solving, and whether it's in homework or on a test, this can almost be a trick question, but don't let it be a trick question. If you're supposed to find the height above Earth for an orbiting object, then you simply subtract the radius after solving for the orbital radius. So if you're solving for the orbital radius, it's always from the center of the large mass being orbited. If you want to know the height above the surface, you better subtract off the radius, not the orbital radius, the radius of the large central mass m. Okay, so if it's how high above the surface of the Earth is a satellite orbiting, solve for the orbital radius. Then subtract off Earth's radius. The mass of a central body can be discovered with quantities that we can measure. And you can't just measure the fact that the Earth is 6 trillion kilograms. You can't put it on a scale, obviously. But you can weigh the Earth. We start with our basic premise, and we're going to have an object orbiting the surface. I know this doesn't look like it's on the surface, but it is, or very near, within 100 miles, say it's good enough. M4 pi squared r over t squared equals gmm over r squared. And what we want to do, we don't care about the mass of this, but by setting these equal, we can solve for big M. So that's what we're going to do. So big M equals 4 pi squared r cubed over gt squared. And that'll give us the mass of the Earth, or whatever else we're trying to find. If you happen to know the radius, and you happen to know the period, how long it takes for the object to orbit. So as I've implied, I think already, don't memorize all this. You know, look how easy it was to derive any particular thing that we needed. You start with Fc is equal to Fg, and you simply go from there. And hopefully that adds some power to your satellite problem-solving repertoire. Catch you in the next video.